All right, team, let's kick things off. For today's brown bag, we're going to really nail down two of the most critical and honestly most mixed up concepts in what we do: concurrency and parallelism. Getting this right isn't just academic, it's the bedrock of building systems that actually perform and scale.
Okay, quick heads up. I used an AI tool to help synthesize the core ideas for the session from a ton of expert sources. Now, I want to be crystal clear. This isn't AI slop. This is distilled signal. Think of it as a tool that helped us cut through the noise to get straight to the good stuff.
You know, if you only remember one single thing from our chat today, make it this quote from Rob Pike. It is just perfect. Dealing with versus doing. That simple difference is everything. It's going to be our North Star for this whole session.
So here's the game plan. We'll start with that core idea, dealing versus doing. Then we'll use some simple analogies to make it stick. After that, we'll peek under the hood at the illusion versus the reality, see how hardware is the ultimate boss, and then wrap it all up with how this stuff actually applies to our day-to-day engineering work.
Okay, let's dive right in. The main idea in this first part is that we're talking about two completely different things: how we structure our code versus how that code actually executes on a chip. So, concurrency. This is all about design. It's a choice we make as engineers. It's how we break a problem down into smaller, independent pieces that can run on their own. The key word there is can. This is a property of your code, your software structure. You could write a concurrent program on a machine with just one single core.
Parallelism, on the other hand, that's not about design. That is a runtime reality. It's the hardware literally doing multiple things at the exact same time. And for that, there's no way around it. You absolutely need more than one core. It's a physical thing.
This table really lays it all out. See? Concurrency is about structure, dealing with tasks by interleaving them, and its main goal is making things feel responsive. Parallelism is about execution, doing things simultaneously, and its goal is raw throughput, getting more work done. Here's the most important relationship to remember. A concurrent design creates the opportunity for parallelism.
All right, enough with the abstract definitions. Let's build a gut feeling for this. A solid mental model is what's going to make these ideas actually useful when you're coding.
So, how do we picture this? Let's imagine something we've all seen, a coffee shop checkout line.
Okay, first, picture one, single, incredibly efficient cashier. They start taking customer A's order. While A is digging for their wallet, the cashier instantly switches over to customer B and starts their order. They are dealing with two customers at once, making progress on both by rapidly switching between them. But at any single instant, they are only doing one thing. That's concurrency.
Now picture two cashiers at two registers at the exact same microsecond. Cashier 1 is helping customer A and cashier 2 is helping customer B. This isn't dealing with tasks anymore. This is doing two tasks at the same time. That's parallelism, and it requires more resources, a whole other cashier and register.
That single cashier example is a perfect lead-in to this next part, because how does a single-core computer create that illusion of doing multiple things at once?
Well, the magician behind the curtain is your operating system scheduler. It uses this technique called preemptive multitasking, which is just a fancy way of saying it switches between tasks incredibly fast, giving each one a tiny slice of CPU time. It happens so quickly, it feels to us like our music, our browser, and our code editor are all running at the same time. But, and this is a huge but, that magic trick has a cost. Every time the OS switches tasks, what we call a context switch, it's not free. It takes about 5 microseconds. That sounds tiny, right? But to a modern CPU, that's tens of thousands of cycles where no useful work is getting done. It's pure, unavoidable overhead.
And that overhead is what drives our strategy. Concurrency is a lifesaver for I/O-bound work. If a task is just sitting there, waiting for a network response, the OS can switch to another task and keep the CPU busy. It makes the system feel fast. But for heavy, number-crunching, CPU-bound work, we want true parallelism. We want to avoid those costly context switches and just maximize raw computation.
Which brings us down to the metal. At the end of the day, our software doesn't run in a magical cloud. It runs on physical silicon, and the rules of that hardware are the ultimate arbiters of performance.
The most important hardware reality is the memory hierarchy. A CPU core is insanely fast. Main memory, or RAM, is painfully slow in comparison. To bridge that massive gap, the chip has these tiny, super-fast caches. Getting data from the L1 cache takes a few cycles. Getting it from main memory can take hundreds. Effective parallel code is all about keeping the data each core needs as close to that core as possible.
And this hardware fact leads to some really nasty, hard-to-debug performance bugs. The most infamous one is called false sharing. So imagine one thread on core 1 needs to change variable x, and another thread on core 2 needs to change variable y. Logically, they're totally independent, right? But if x and y happen to be neighbors in memory on the same 64-byte cache line, the hardware gets confused. It has to shuttle that entire line back and forth between the cores, completely serializing your parallel code and absolutely tanking your performance.
Okay, that's enough theory. Let's bring this home. How do we take all this and turn it into real, actionable strategies in our daily work? Well, first, we need a dose of reality from our old friend Amdahl's law. What this law proves, mathematically, is that your performance gains are always limited by the part of your program that can't be parallelized. If even 10% of your code has to run sequentially, you will never ever get more than a 10x speedup, even if you have 1,000,000 cores. That serial portion is the ultimate bottleneck.
So this leads to a very clear playbook. If your tasks are I/O bound, waiting on databases, APIs, the disk, you want concurrency. You should use more threads than you have cores, so when one thread is blocked and waiting, another one is ready to jump on the CPU. But if your tasks are CPU bound, just pure computation, you want parallelism. The goal is one active thread per core to just crunch numbers and avoid context switching overhead.
And that leads us to the classic question, okay, how big should my thread pool be? Well, there are some pretty standard formulas that give you a great starting point. For CPU-bound stuff, it's easy, number of cores. For I/O-bound tasks, it's a bit more complex, factoring in how much time is spent waiting. But let me be clear, these are heuristics. They are a good place to start, but you must always measure, profile, and tune for your specific application.
And finally, we have to talk about the bugs. Writing concurrent code introduces whole new classes of problems that are notoriously painful to track down. You've got race conditions, where your program only works if threads run in a specific lucky order. You've got deadlocks, where two threads get stuck waiting for each other forever. And you've got starvation, where one poor thread just never gets the resources it needs to run.
So I'll just leave you all with this one last thought. Concurrency is the design. Parallelism is the execution. By designing our systems to be concurrent today, we're making them ready to actually take advantage of the increasingly parallel hardware of tomorrow. So the question for all of us is, are our designs ready? Thanks, everyone.